Good morning, everyone. Hope you're doing well today. First, let's go over the homework answers. Most of you did pretty well. A few of you have some issues that you need to look at. All right, so the first one, seems I got this PowerPoint in the wrong place. I thought I had it where we needed to be, so let me get us in the right place. Okay, here we go. All right, so first one, 1B was just a half reaction. So remember, it's always E equals E0 minus 0.0592 over N log products over the reactants. Almost everybody did this one right, so that answer is 0.60 volts. Okay, then 2B was another half reaction. Slightly harder because you had to know that this is a 2 here, which means this concentration is going to be squared. Okay. And so that answer should be minus 0.13. Okay, then 3 has to do with whole reactions. So they give you the cell notation. And you can do this two ways. You can do the two half reactions, or you can write a balanced reaction. I'm going to show you both, but again, you only need to know how to do this one way, as long as you can do it correctly. So the half reactions, the first one is the mercury 2 plus going to mercury, and we calculate E for that half cell. And then the other one's a little bit more complicated. That's this vanadium reduction, and we calculate E for that. Now, notice both of these are written as reductions, always as reductions when you do these. Okay, then E cell, cathode minus the anode. And you should get a minus 0.6 volts. This one also asked, is the cell electrolytic or galvanic? If you get a negative number, it's electrolytic. A few of you got positive 0.6 and then told me it's electrolytic. Okay, that's not possible. So electrolytic, E cell has to be negative. All right, if you do it the other way, then you're going to combine these two half reactions for a balanced reaction. This one is the anode. How do I know that? On the left, anode always on the left. So I need to flip it around when I combine those. And this is the balanced reaction. Then I calculate E standard. So that's the cathode minus the anode. And then just do one Nernst equation where I put all the concentrations in. Okay, notice you get the same answer, and it's electrolytic. And again, I don't care which way, whichever one you're more comfortable with. Most of you, it's probably better to do the half reaction. Okay? That's a little bit simpler, but it's more calculations. All right, and then 3C, same thing. We can do the two half reactions. So the iron 3, again, both of them as reductions, going to iron 2, and tin 4 going to tin 2. You put in the concentrations, and then cathode minus the anode, and you should get minus 0.84. And again, this is electrolytic. Okay, if you want to do it the other way, combine those two. Again, calculate standard cell potential and do one calculation, same answer. Okay, so that was the homework. On the quiz or exam, we will not have questions like these, but you do need to know E cell is cathode minus the anode, and you need to know how to use the Nernst equation. And we're going to see that today when we get into chapter 7. All right, we have just a little bit of chapter 6 that we didn't have time for last time, so let's first finish that up. We need to talk a little bit more about reference electrodes. So remember, we're always measuring a potential difference, a potential of something compared to something else. And we talked about everything we measure in the table is always compared to SHE. But the SHE is It's a good reference electrode, but not easy to use. And what do we, when I say good reference electrode, what do I mean? Well, a good reference electrode is one that has a fixed potential, the same potential all the time and at different temperatures, that's stable, that can, if you apply a small current, the potential will go back to that standard value, and it follows the Nernst equation. Okay, and so of course that SHE is an important reference electrode, but for use every day in the lab, it's impractical. You have to use hydrogen gas, it has to be at a constant pressure, and hydrogen gas is flammable. So what's actually used today as reference electrodes are two other kinds. Okay, so one of them is the silver-silver chloride electrode, and the other one's called calomel. So we want to look at these two quickly. So calomel is the one that came after SHE. So this is the second oldest, and it was very important for many decades. And its calomel is based on this compound. Okay, this compound, mercury 1 chloride, is also called calomel. Okay, it has two names. So the half reaction is the calomel gaining 2 electrons, going to chloride ions and mercury as a liquid. And notice the half reaction for that would look like this. Okay, now notice this mercury Hg2Cl2, the calomel, is saturated. That again means most of it's a solid, but a little bit will dissolve in solution, a very little bit. And it is always going to be saturated, the calomel. Okay, then we also have some chloride ions that come from KCl, and the concentration of that can change. So notice that the E for this half reaction only depends on the concentration of the chloride. Okay, the mercury is a liquid, the calomel is a solid, so E doesn't change with those, only with the concentration of chloride. In addition, the calomel electrode is quite sensitive to temperature. So if you change the temperature, you will change E for this. The most common version of this is what we call the saturated calomel. It's abbreviated SCE. Now, that saturated, if we go back here, remember the calomel is always saturated. So if I say saturated calomel electrode, what's saturated is the KCl. Okay, it's referring to the KCl. So the way this looks, we have some mercury as a liquid, and then they have some mercury chloride, the calomel here, the solid, and then they have a plug. And then in here, we have KCl, and notice there's KCl solid in this because this is saturated. So this is the way that you would design this electrode. And notice the E for this half reaction is 0.244 volts. Okay. Now we can use other concentrations of KCl, but like I said, the most common is saturated, the SCE. One problem is sometimes this can get dried out or plugged. You get a reaction and solids form there, and then it doesn't work very well anymore. And the calomel, again, has a big problem with temperature. If you change temperature, notice this chart shows you, let's look at saturated SCE. These are its potential, and notice potential changes with temperature. But if you change the temperature of your reaction, the calomel is very slow to respond. It takes a long time to get to the new potential. So if you're working at different temperatures, calomel is not a good choice. But other than that, it's a pretty good reference electrode. All right, so that was the second major reference electrode. And then the next one that came was the silver-silver chloride. This one is now the most common. And so notice what we have. We have a piece of silver wire with some silver chloride. And then again, there's going to be chloride ions here. Again, the silver chloride is saturated. The KCl can have different concentrations. If the KCl is saturated, then its potential is 0.199 volts at 25 degrees. Okay, so notice here they've got a couple, they've got the saturated, and then if the KCl is 3.5, has different potentials. Again, for both of these, the most common is the SCE, saturated calomel electrode, and saturated silver-silver chloride. Okay, silver-silver chloride is very easy to make. You can make it yourself. It's a reliable, and it's better than calomel because calomel has mercury, which of course is toxic, and silver is not. Okay, so those are the two most common reference electrodes that are used today in the lab. Okay, SHE is important, but it's not commonly used. All right, a couple of things about using them. This one just shows both those two reference electrodes. First, the level of liquid inside the electrode always needs to be higher than what you're putting it in. If the solution is higher, say the reference solution was here, what would happen is the solution from the outside would try to go into the electrode to make them the same, and that would contaminate your electrode. So you always need to make sure that solution on the inside of this electrode is higher than what you're going to be putting it in. Another big problem with both of these electrodes is they will plug. It's often the species, either the mercury or the silver, will react with ions in solution. You know, if there's silver here and there's chloride or iodide or fluoride, those react and plug this electrode so it won't work. If there's sulfur, that will react with both silver and mercury. So what they do to avoid this plugging problem is they often use something called a double junction. So this is the main part of the electrode, and this solution contains something that will not react. And then this is what you're going to measure out here. And now if this has sulfide or chloride, it's not a problem because the silver or mercury are here. Okay, so that's reference electrodes. Okay, so that finishes up what we need to say about chapter 10. Chapter 10, that's in my other class, chapter 6. This last one just shows you that these concepts of electrochemistry are used for a lot of different electrochemistry methods. We're going to just look at a couple. We'll look at one in chapter 7, and then we'll look at a couple in chapter 8. But just know there are a lot of methods that come out of this electrochemistry. Okay, so now let me get out of that PowerPoint. And we'll switch over to our main topic for today, which of course is going to be chapter 7, which is called potentiometry. Okay, so anytime you see this tree at the end, that means to measure. So potentiometry measures potential. And we know from the Nernst equation that potential is related to concentration. So we are actually, in this method, going to determine concentration by measuring potential of a galvanic cell. So these are going to be spontaneous cells. So to do this, we need two electrodes. Okay. The first one is called the indicator electrode. So this is the electrode that responds to whatever I'm measuring. It responds to these concentrations that I'm trying to measure. The other electrode is a reference electrode. And the reference electrode will always have the same potential no matter what's in solution. And in fact, you already should know what the reference electrode will be. We just talked about the two most common. Okay, remember them? Okay, we'll come back to that in just a minute. But first, let's look a little bit closer at potentiometry in general. So we're going to measure E cell, and we're going to do it under conditions of negligible current flow. Okay, this word negligible means it's so small we can ignore it. It's almost zero. Now, the current cannot be zero, but it's very, very close to zero. It is a very, very small number. And we do this because then the concentration that I'm measuring will not change. Okay, so this method is a non-destructive method, and it's a very simple method. It's a very inexpensive method. You used it in the lab, and it's a quick, easy method to perform. Okay, so we said we're going to use this indicator electrode and a reference electrode. All right, so what are the reference electrodes? Two most common reference electrodes that are used are, I just told you, calomel, usually the SCE, and silver chloride, okay, with these reactions. All right, and both of these are reversible. They follow the Nernst equation, and they have stable potentials with time. Okay, so which one should we choose? Well, as I said, if you have temperatures that are going to change, silver chloride is better. Silver chloride is also safer, better for your health than mercury. But silver reacts with more things. Silver reacts with the halides and sulfides. Mercury reacts with sulfides. So if you know you've got halides, then sometimes SCE might be better. But if you're not measuring with halides, then often silver chloride is better. Okay, so this potentiometry experiment, we said we're going to measure potential, and that's going to tell me about concentration. Really, it tells me about activity, but remember, we're going to use concentration. So you take these two electrodes, okay, and the reference electrode and the indicator, and you connect them to a meter, like is shown in this picture. And we're going to measure E cell up here at the meter. And remember, this is always true. E cell is cathode minus the anode. Now, usually in potentiometry, the reference is the anode. So then this equation is E cell is the indicator electrode minus the reference. But sometimes they actually switch these, okay, so that the reference is the cathode. So then the equation is reference minus the indicator. Okay, so it can be either. And you say, well, how do I know? Well, you have to look at the cell and see how is it set up. Which one is the anode, which one is the cathode. But remember, it's always going to be cathode minus the anode. Okay, so this indicator electrode, we said it responds to whatever I'm trying to measure. And it has a couple of other names. Okay, this AKA, do you know that term? It's also known as, so sometimes we call it the working electrode, and sometimes they call it the sensing electrode. So they're all the same thing, indicator, working, sensing. All right, and these indicator electrodes, there are two big categories. Okay, the first one is metallic, and the second one is membrane. So the first ones that were developed were metallic. So these were first, but they're not used much anymore, but we still want to just understand the basics about them. So we'll look at the metallic electrodes. There are 4 types of metallic, and they have very difficult names for you to remember. Okay, they are the electrodes of the first type, electrodes of the second type, electrodes of the third type, and then redox electrodes. Okay, so actually quite easy to remember the 4 types: first type, second type, third type, redox. Okay, so the first type is when you have an active metal that indicates its own ions. For example, Okay, I have a piece of copper metal, and we're going to use it to measure the concentration of copper 2. Okay, we know E for this half cell looks like this. So notice if I measure E, that tells me about concentration of copper 2. So to set this up, remember, 2 electrodes. There's the indicator and the reference. Here, the indicator is simply a piece of copper wire in a solution of copper ions. And then here's my reference electrode. Okay, so this is the E for the copper reaction. Now, when I measure this, remember, what do I measure? Do I measure E of copper? No, I measure E cell. So remember, E cell, cathode minus the anode. So the cathode is the copper reaction, and the anode is the reference electrode. So this copper, E copper, is all of this right here. That's going to go right there. And then minus E of the silver chloride, or the SCE, whatever that is. So that's how we would set up the equation. And again, I measure E cell, it's going to tell me about copper 2 concentration. All right, now these electrodes are very simple, and one big problem is other ions can also reduce a copper. Anything that has a higher E0, like silver or mercury or palladium, which means if those are in my solution, I cannot measure just copper. I'm going to also measure these. I'm going to get interferences. So this kind of electrode, they're very simple. Look at the picture. Piece of wire in a solution. That is very simple, but they're not selective. Lots of other things can be reduced at the electrode. Also, some metals will react with oxygen if they're in solution. So we always have to remove the oxygen from the solution so that doesn't happen. Also, we have to control the pH. If the pH is very acidic or very basic, sometimes metals will react with those or dissolve or form precipitates. So we have to control the pH for these. Okay, so this one is actually practically not very useful. The 2 most common ions are to determine silver and to determine mercury 2 at a mercury electrode. Okay, so that's the first type. All right, the next kind, second type. So here you have a metal, and it's going to be in contact with a precipitate, a solid that contains that metal cation. And this one responds to an anion. So for example, okay, I have silver chloride, the reference electrode. And notice that it's got this anion, chloride. So if we set up the Nernst equation for this half reaction, notice E tells me about the concentration of chloride. Okay? So this one, the metal, responds to an anion from its salt. So we would set it up like this. So again, I have my reference electrode. I have a piece of silver wire. I put some silver chloride coating on it. And then I've got chloride ions in the solution. So I'm going to measure E cell. And remember, E cell is cathode minus the anode. So the silver chloride is there. That whole thing's going to go right there. And then the reference is that, whichever is there, the silver chloride or SCE. So this is second kind. So the silver chloride reference electrode is a second kind electrode. What about SCE? It's also second kind. Mercury responds to chloride from the mercury salt. Okay, so that's second kind. All right, the next one is the third kind, and this one's the most complicated. So this one you have an ion, and you have a metal electrode that responds to an ion that's not the same and not from a salt of that metal. So there's actually two equilibriums, and you have two salts. So the cation that it responds to is different than the metal cation. All right, so for example, if I have mercury with EDTA, mercury EDTA will form a complex, but the EDTA will also form a complex with calcium. So the way this works is you wind up with this mercury electrode responding to calcium. So there's two solids and then a metal that responds to something totally different. Another example, zinc and zinc oxalate. Okay, this oxalate will also bind to calcium. So you have two solids, the zinc oxalate and calcium oxalate, and you have the zinc electrode responding to calcium ions. Okay, now these electrodes are complex and they're sluggish and unstable. They're very slow to respond, they're not stable. So this is a kind of electrode, but really it's not useful. You will never use this kind of electrode. There are just a lot of problems with them. All right, and then the last one is what we call redox electrodes. So here you have an inert electrode, and it's not part of the redox reaction. The electrode is only the place for the electrons to be transferred. So for example, we could have iron 2 reacting with permanganate. And so you have the iron being oxidized and the permanganate being reduced, and the electrode is simply the place where the electrons are transferred. Okay, so you measure that ratio. These are actually commonly used, these redox electrodes. So just using the electrode as a place for the electrons to be transferred. Okay, so that is the 4 kinds of metallic electrodes. We want to now look at a sample calculation because this kind of calculation will be in your homework. It will be on the next quiz, and it will be on the final exam. So you need to know how to do this kind of calculation. So notice that I have one of these metallic electrodes. Which type is this? Notice I've got a metal and a salt and an anion. So this is second type, okay? So they tell us that we know the cell potential for this cell. They've set it up and measured it, and we want to know what is the calculation, what is PBr, minus the log of the bromide ion. Okay, so where should we start? Well, remember, it's always E cell is cathode minus the anode. Okay, so here, which one is the cathode? Is it the copper reaction or the SCE? Okay, well, notice it's the SCE. And how do I know that? It's on the right. Remember, the cathode is always on the right. The anode is always on the left. So remember, I told you, usually the reference is the anode, but sometimes they switch it. And how do you know? We look at the cell diagram. All right, so E of the cathode is going to be this E for SCE. Now, what's E of the anode? Well, this is where I have to use the Nernst equation, okay? So I'm going to need to do the E0 minus 0.0592 over N log products over the reactants. Okay, so E cell is going to be E of the cathode minus, okay, notice it's minus the E0 minus 0.031 minus 0.0592 over 1. Notice N is 1 here, and then log of the bromide. Okay, so now we're going to put in the numbers. So they gave us the cell potential that goes here. We know this E0 for SCE, that's a constant at 25 degrees, that's 0.244 volts. And then we have this. Okay, so now what I need to do is just do fairly simple math. And remember, p bromide means minus the log of the bromide concentration. Okay, so we'll have to bring this over here and bring this over here. And I would multiply it by 1, divide by 0.095. And so if you do all that math right, you should get 2.38. And that would be your answer. Okay, so it would be a good idea for you to later just practice this equation. Make sure you can do this math to get this answer. You don't actually have to do any logs for this. You're actually solving this for minus log. Okay, so the math is actually quite simple. You just have to watch your signs as you're bringing things over. Okay, so these metallic electrodes, they are historically quite important, but they're not used much today because they have pretty poor detection limits. And there are better systems, okay? Those inert electrodes used in the redox titrations, that's the one place where these are still commonly used. Okay, but in general, there's better systems. If I want to know the concentration of chloride, there's a better system than these metallic electrodes. Okay, so what is that better system? Well, it's the other kind of electrodes that are called membrane electrodes. So these are a little bit harder to understand, but much more common today. So here you actually have a membrane that responds to differences in concentrations. So the most common kind of membrane is actually glass. So if you can imagine, you have this thin layer of glass, and we have one concentration of hydrogen here and a different concentration here. So what's going to happen is we're going to get some movement of ions to try to make those concentrations the same. And you wind up getting a kind of junction potential as these ions move through the glass to try to balance this charge difference. Now, this potential difference is actually called a boundary potential. And this boundary potential, as we're going to see, is directly proportional to the concentration of the ion, okay, in this case, the hydrogen ion. So that potential difference we get at this membrane is going to tell me about the concentration of the ion I'm trying to measure. Okay, so as I just said, the potential difference is related to the concentration difference of the ion you're trying to measure. Now, this does not involve a redox reaction. There is no electron in these reactions, okay? No electron transfers. So usually these kinds of membrane electrodes, we actually call them an ion selective electrode, ISE, because they respond to ions, okay? ISEs. And there are 5 kinds of membrane electrodes, but we are only going to talk about 2 of them. We're going to talk about the glass membrane in a lot of detail, and then we'll talk about solid, but there are also some membranes that are liquid. There are some that can sense gases and some that use enzymes. Okay, but you don't need to know these other names, but these 2, the first 2 are the ones we'll talk about. Okay, and the most important by far is that glass electrode, that its biggest use is to measure pH. Okay, if you have ever measured pH in the lab, okay, with an electrode, this is the method that you have used. You have used potentiometry. And you will see that it's actually much easier to do this experiment than to actually understand the experiment. Okay, now one note before we get into the theory. These ISEs, ion selective electrodes, they have limited detections that are from 10 to the minus 5 to 10 to the minus 12. Okay, these are pretty small numbers. So usually, like if we're measuring hydrogen ion, and instead of talking about these small numbers, we talk about pH, which remember is minus the log of the hydrogen ion concentration. So these ion selective electrodes, instead of measuring concentration in molarity, we usually measure them as what we call the P ion, okay, where P ion is minus the log of the ion concentration in molarity. Okay, so we'll talk about PCA, that's minus the log of the calcium ion, or PF, POH, PCO. Okay. So we always talk about these concentrations as P ions, okay, instead of molarity. Now remember, a P ion has no units. Okay? We don't talk about units for that. You know, we talk about a pH of 7. No units, just 7. Okay, now let's look at the theory. So again, we're going to focus on the glass membrane electrode. So we have this very thin piece of glass, and we have one concentration of hydrogen here and a different concentration here. And again, we're going to get this potential that develops right here at the membrane called the boundary potential. And that boundary potential is going to tell me about the concentration of the hydrogen ion. So let's look at the setup. Now, this is the same as, as we talked about these indicator electrodes. So this is still 2 electrodes. We're going to have an indicator electrode and a reference electrode. So notice here, I've got an SCE, my reference, and then this is the indicator with its thin piece of glass right here. This is the glass membrane. And this is the cell diagram for this whole cell. Okay, and you look at this and you think, oh, it's very complicated. And it looks complicated, but it's actually not so bad. So let's look at what's here. So first thing over here, notice as the anode, we've got the reference electrode, SCE. Okay, then a line. Now we're coming into the solution. This is the solution that I want to know. What is the pH of this solution? What's the hydrogen ion in this solution? So that's right here. That's my analyte. All right, now I have that glass membrane. So they put the membrane there. And now I have a solution inside the glass membrane, and it will have some hydrogen ion in it. So that's this concentration right here. And then notice on the inside, they have silver chloride. Oh, that's another reference electrode. Okay, so these cells, notice they're different. There's actually 2 reference electrodes. There's one on the outside and one on the inside. And so they show them both here in the cell diagram. Okay, so we'll look at that in more detail. But first, a couple of things. So this is showing it most clearly, but today, usually what they do, instead of having 2 electrodes, is they actually combine them into 1 electrode. This is called a combination electrode. And so here's that glass membrane. And then notice on the inside, there's actually 2 silver chloride. And the reason they do this is because this is now just one of those, and so it's much easier to put into things than to have 2. Okay. So usually today, most of them will use this combination. But it's a little bit harder to talk about this way, so we'll actually talk about it this way. But the cell diagram would be similar for these 2 things. Okay, so this glass membrane that we're going to be talking about. Let's first talk about what is it chemically. Okay, so the glass is primarily SiO2, silicon dioxide, but it's got some sodium oxide in it and some calcium oxide. So this is what the structure looks like. And on the surface of that glass, you're initially going to have a lot of sodium ions. Now, in order for this to work, the first thing you have to do is what we call hydrate. So you have to take that piece of glass electrode and you have to put it in water. And what you're going to be doing then is this exchange reaction. You want to take all of these sodiums that are at the surface and you want to replace them with hydrogen. Okay, so we get all of that surface with hydrogen ions instead of sodium ions. Okay, that's again called hydration. We're hydrating it. All right, so now remember, on one side I have that internal solution with some hydrogen ions, and then on the outside I have that solution I want to measure, and it has a different hydrogen ion concentration. And remember, there's going to be movement through the glass to try to make those hydrogen concentrations the same. So if you're very close to the surface, the hydrogen ions will be what moves. But as soon as you get into the inner part of the glass, it's actually the sodium ions that will move through the glass. Okay, now remember that glass also has calcium, but calcium is big, and so the calciums, they don't move. They just stay in the place. Okay, so you have hydrogen ions moving at the surface, and then sodium ions moving through the glass to try to get these concentrations the same. Okay, so back to this picture. Okay, so the side that has more hydrogen ions, and sometimes it'll be the internal solution, sometimes it will be the external. It can be either. Okay, here it's showing the internal. So the hydrogen ions will move, the one that has the more hydrogen ions, remember they'll move at the surface, but then inside the glass, it's the sodium ions that actually move across the glass to create this charge difference. Okay. So by those sodium ions moving through the glass, we're going to get a potential difference at this membrane that's called the boundary potential. Okay, the boundary potential. And I already told you this boundary potential is going to tell me what is this hydrogen ion concentration. Okay, so let's go back to this picture now. All right, so we've already looked at the cell diagram and said we have my reference, and then I've got that glass membrane here. Okay, so notice I have several potentials here. This reference electrode on the outside, it has a potential. And then because the concentration inside and the concentration here are different, you're going to get a junction potential right here. All right, and then we get one potential on the inside of the glass, and then we have a different potential on the outside, okay, from the ions moving. Okay, that difference between those on the inside and the outside, that is this boundary potential. And then I have the internal reference electrode, and it's going to have a potential. Okay, so when I measure E cell is going to be a combination of this outer reference electrode, of the inner reference electrode, and the boundary potential, and the junction potential. Okay, so E cell is going to have all of these potentials combined. Now, we know that this outer potential, that's a constant. It's a reference. The inner reference, that's a constant. The junction potential, we're going to say it's a constant. Now, this is not always true, but it'll be easier for us if we say the junction potential should always be about the same. So we're going to treat that like it's a constant. Okay? And then we'll have this boundary potential that, again, is going to tell me about the hydrogen ion concentration. Okay? All right, so let's take a break there, and then we'll continue with how are we going to put this all together to do a measurement. So 5 minutes. Okay, so now we want to take this and actually develop an equation for how does this boundary potential tell me about this concentration that I'm trying to measure. Okay, so we won't get into the complicatedness, but I'll just tell you that from thermodynamics, you can actually show that this boundary potential is related to this equation, okay, where H1 is what I'm trying to measure. That's my analyte concentration. And H2 is the concentration on the inside. And that's the concentration of hydrogen on the inside of that glass. So if that concentration on the inside is a constant, and it should be because you can't really get inside that, it's a sealed glass, then this equation can simplify to this, where notice what I have. This boundary potential is equal to a constant minus 0.0592 pH. Okay, so notice the boundary potential is directly proportional to pH, okay, which is what I've been telling you. Okay, well, that's great, except when I go into the lab, when I set up that cell, what do I measure? Do I measure the boundary potential? No, I measure E cell. Okay, so what I really need is an equation for E cell with this hydrogen ion I'm trying to measure. All right, so we'll start here with the equation we just had. Boundary potential is a constant minus 0.0592 minus pH. Now we said we're going to measure E cell. And remember, E cell is the indicator minus the reference plus the junction potential. All right. Now, that indicator, remember, is the boundary plus that second reference. Okay, if we go back here, okay, remember this whole part right here is the indicator electrode. So from here to here. So the indicator electrode's this boundary plus this inner reference. Okay, so now let's take all of this, and we know the indicator is this, we know the boundary is this, and if we put them all together in one equation, this is what we get. When we measure E cell, it's this constant minus the 0.0592 pH plus the reference 2 minus reference 1 plus the junction potential. All right, now if you just look at this, you think, oh, that's a very long equation, very difficult. But let's think about what do we know? Okay, this is a constant. This, constant. This, constant. This, we're going to say it's a constant. So notice this complicated equation becomes E cell is a constant minus 0.0592 pH. So when I measure E cell, again, that's a direct relationship. It's a direct measurement of the pH of that external solution. Okay, so that's great, all right? And so when we talk about any of these ion selective electrodes, right now we're looking at pH, the equation is always this. E cell is a constant minus 0.0592 pH. So we've got this glass membrane electrode. We're going to connect it to a reference electrode and a meter. We know that both the half cell and E cell are related to pH. And again, what you measure is always E cell. Okay, now notice that we could actually plot this on a graph. Okay, what would we put here? If this is my equation that governs E cell, and this is an important equation, then if we make a plot of E versus pH, okay, remember, general calibration is always signal versus concentration. Well, here my signal is E, and my concentration is in the form of pH. Okay, and notice that the line I get would have what they say is a Nernstian slope. Okay, notice the slope would be minus 0.0592. Now, you've seen that number before. Where have you seen that number? The Nernst equation. So they call that a Nernstian slope. And then notice the intercept, okay, where that intercepts this axis right here, that is your constant. Now, remember the Nernst equation was E equals E0 minus da-da-da-da. This is not E0. Remember, there is no redox reaction. This is K. This is a constant. Okay? It's not E0. Okay, so that's the equation that governs this. Now, when I want to practically use this, I'm going to calibrate it with buffers. Okay? So what is a buffer? Well, a buffer is a pH standard. Okay, these are solutions that you know their pH. So we're going to use these buffers to set the values of K and to set this slope value. Okay, now you say, oh wait, we know the slope. It's minus 0.0592. Well, that's actually the theoretical slope. The real slope might be a little bit different, so we have to set that. Okay, so first the buffers. As I said, these are solutions that you know the pH. So you can buy these buffers from companies, and they come and they'll tell you, you know, this buffer. Well, actually, if you're in America, they will tell you that this buffer that you buy, its pH is 7.00. If you are in China, this buffer's pH is 6.86. I don't know why it's different, but it is. If you're in your own country, I don't know what it is. You need to read the bottle and it will tell you. Then there's another buffer that has a pH of 10 or 10.01 and one that's 4 or 4.01. And in America, we even make them colored so you can very easily get the right one. In China, there's usually no colors. You have to read the bottle. Okay, so you're going to use these buffers, the pH standards, and your meter will have either 2 or 3 controls. So one of the controls says calibrate, and one of them says slope. If you have a Chinese meter, this is what it will say. Some of the meters have a third button that says temperature. Okay, so the first thing you're going to do is if your meter has a temperature button, the first thing you do is set the temperature. And remember, this 0.0592 comes from that Nernst equation where T was 25 degrees C. So if you have a different temperature, you set the temperature to set this theoretical slope. Now again, this is theory. The real slope may be a little bit different. Okay, so set the temperature if your meter has that. If it doesn't, that's okay. The next thing you're going to do is take that 7 or 6.86 buffer, always that middle buffer, and you're going to use the calibrate knob. And what this does is it fixes K. Okay, so it's going to set K. You're going to use that buffer to set where this K should be for your meter. All right, that's the first buffer. Now the second one is to take a different buffer, usually 4 or 10. Usually if you're going to be measuring things that are acidic, you use 4. If you're measuring things that are more basic, you use 10. So you're going to take the second buffer. Let's say you take the 4. And now you're going to use that buffer to set the correct slope. So we're going to keep that first one, that 7 or 6.86 at that exact point, and then we're going to change the slope with the second buffer. Okay. All right, so this sets the actual slope, not theory, the actual. Okay, now I said, you know, the slope should be close to this, but often it's a little bit different. Okay, why? Well, the first reason is we already talked about. That number comes from a temperature of 25 degrees C. So if your temperature is a little bit off of 25, the slope's going to be a little bit different. The other thing is, sometimes the electrode itself, the way it responds, is not perfectly according to this equation. If there's impurities in the glass, or the electrode is a cheaper electrode and the construction is not good, then sometimes you will not get the exact slope of 0.0592. So many electrodes have pretty good quality, and they have what we call a Nernstian slope or Nernstian response. That means their slope really is 0.0592. But there's other electrodes, maybe a little bit lower quality, and they don't give you 0.0592. They give you maybe 90%. Okay. So if you only use one buffer and you only fix K, then you may have a lot of error if you don't have a really good quality electrode. So always you use two buffers to calibrate these pH meters, one for slope and one for K. Okay, so this is a picture of one of the meters that you've probably used in the lab, unless they changed them in the last couple of years. So notice this one has a button, and then this is the temperature, and here's the, I always have to look at it, make sure I get it right. This is the slope, and this is the calibrate button. So you set the temperature and put it in and adjust and adjust. Some meters might look like this. This one is a little bit more expensive meter, and this one's more automatic. So you actually tell it, I want to calibrate, and then it'll say, okay, give me the 7 buffer, and you put it in and it adjusts it. Now give me 10, and it adjusts it. It goes through the same process. This one's more automatic, this one's manual. Okay, so that's the theory. Now we need to talk about some of the errors that you can have in a pH measurement. The first one is the pH measurement is only as good as your buffer. Okay, if your buffers are old, maybe their pH has changed with carbon dioxide or mold growing in them, or people got impurities in them. So if those buffers, those standards are not correct, you're going to get a bad measurement. A pH can only be done to about 0.01 units. If you just need to measure pH, you know, sometimes someone says, oh, my pH is 7.375. Okay, they don't know what they're doing. You cannot measure that last figure that accurately. You can't. You can only measure to 2 decimal places. Now, if you're measuring the difference between 2 solutions, you can measure to 3 significant figures, okay? But you cannot measure accuracy to 3. Another error is the junction potential. Okay, you remember we said that the junction potential is a constant. It's the same. And if your buffers and your unknown have very different ionic strengths, then the junction potential is not the same, and you're going to introduce an error. Okay, so that's the junction potential. All right, another error you might have is something called the alkaline error. And this occurs, or it's also called the sodium error. So alkaline means very high pH. Like if the pH is 12, you're going to have an error. Now, let's look at what's going on. We have a pH of 12, so that would be a 0.01 molar sodium hydroxide solution. So in this case, the concentration of hydroxide is 0.01. What is the concentration of hydrogen in this solution? You should know this. Okay, well, it's 10 to the minus 12. Remember, pH plus POH equals 14. And remember, 10 to the minus 12 is this. All right, so what this means is, remember, I've got this glass membrane, and now I have a whole lot of sodium and a tiny, tiny bit of hydrogen. Okay, look at the difference in these two concentrations. So what that means is that membrane will actually respond to sodium. Remember, when the glass started, it had sodium, and the first thing we did was hydrate it. We put hydrogen there. So now the glass will respond to sodium. And that's going to make it seem like their concentration is too high or the pH is too low. So this alkaline air, meaning you have a high pH, is going to give you a low reading. So you see that here as we get more basic, depending on the electrode, and when we get out at these very high pHs, we start getting more airs. Okay, so that's the alkaline air. Now notice over here, when I get to very low pH, the air goes the other way. So at low pH, the reading is too high. So this is called an acid air. So this is when the electrode reads higher than the actual pH. And they don't really understand why it does this, but we know that it does. So what that means, that you can really only measure pH down to about 0.05 is the lowest, and then you can't really measure much higher than 11 or 12, depending on the electrode that you have. Notice if you have this C and D, you start getting airs even at 9. Okay, but if you have these better electrodes for pH, you can get up to 11 or 12. So that's the useful range for pH electrodes. Another air is that hydration. Okay, remember we said the first thing we do, soak it in water. And when you're not using an electrode, you should always leave it in water. Okay? If you don't, if you just leave it in the air, then that glass will dry out. And then someone comes, they try to use it, and they will get readings that are jumping everywhere. The electrode is not stable. Okay, so you then actually have to rehydrate it. You have to soak it in water, probably for 24 hours until it will behave itself again. So that's called a hydration air. Okay, now these glass electrodes, we've talked about the theory. And again, the most common use is to measure hydrogen ion. But you can actually use them for lots of different ions as well. What they do is they change the glass composition, the chemistry of the glass, so that it will respond to different ions. And notice there's this whole list here. So you can buy ion selective electrodes that respond to all of these different ions. And usually they will just respond to one kind of ion. They're fairly selective. All of these, the theory is the same. That there's the glass membrane and two different concentrations, and you get this boundary potential. And the boundary potential is related to concentration of whatever you're measuring. Okay. For all of these, you measure E cell. And the general equation is always going to be E cell is a constant minus 0.0592 over N. So remember, hydrogen, there's one electron. Okay, but if you were measuring the iron 3, then N would be 3, or copper 2, N would be 2, and then times P ion. Okay, so again, very important equation that describes all ion selective electrodes. E cell constant minus 0.0592 over N P ion. Okay, so to sort of summarize these glass electrodes, they are really good indicating electrodes in potentiometry. You have to make sure you calibrate them properly, and you have to take care of them. That glass membrane is actually very thin. It's this tiny membrane that we are looking at. And so if you hit it against something hard, it's very easy to break. and then it won't work at all if you break it. Okay, so you do have to take care of them. There are always going to be some errors. Okay, we talked about some of those errors, and so some of them you can't get rid of. And as I mentioned, you can use them for other ions, okay, but the most common use is hydrogen. Most of the time, they're going to be these combination electrodes where we take those two and put them together in one. You can use them in smaller places that way. All right, so as I said, lots of times the most important use for glass is to measure pH. Very easy to use, very few interferences, and a pretty low-cost method. You can use them in lots of different conditions, strong oxidants or reductants, gases, proteins, and they come in all kinds of shapes and sizes. And again, there are some errors you have to be aware of, and we talked about those. Okay, so that's the membrane glass electrodes. So the only other one we're going to look at is the solid state membrane electrode. And again, this is going to be the same theory. E cell is going to be a constant minus 0.0592 divided by N p ion. That's always the equation. So for the solid state, your membrane, instead of being glass, is going to be a solid. It's actually some kind of ionic solid. Here are three common ones. Okay, so this membrane right here is, so let's say, silver chloride. And it's a single crystal or silver chloride that's been powdered and melted and then put under high pressure to make this membrane that we have here. And notice the membranes are pretty small, 10 millimeters by 1 by 2 millimeters. So these are small membranes. And in order to work, this membrane has to contain whatever ion you're trying to measure. So there's some ion here you want to measure, and here. Well, this is the one you're going to measure, and that same one will be here. Okay, so that membrane has to contain that ion. And notice also it cannot be soluble. Now, why not? Well, I'm trying to measure this ion, let's say X, and if this membrane has X and it starts dissolving, that's going to change the concentration of my solution. Okay, so it can't be soluble. All right, so what they do is they take the membrane and they seal it in a tube, and then it's going to work just like that glass membrane. So instead of glass, we have a solid. So we have one concentration here and a different concentration here, and you will get ions moving, trying to make things equal. So you're going to get this boundary potential that forms right here at that membrane. And these can respond to concentrations down to 10 to the minus 6 molar, so they're fairly sensitive. Okay, so the most common one is an electrode that's selective for fluoride. I believe you probably use this one in the lab. So the membrane is made of lanthanum fluoride with a little bit of this guy, EuF2. Now notice it takes only 2 fluorides, where this one takes 3. So if we put some EU in there, we wind up with some holes where we're missing some fluoride. And then that means fluoride can now move through that membrane. So we've got some holes in here now, and the fluoride can move, that way or this way to balance those concentrations. This is pretty selective. The only thing you have to worry about also causing a response is fairly high concentrations of hydroxide. So if your concentration is more than 0.1 molar, that will interfere. And that's a pretty high concentration. So quite selective. Okay, so this table just shows you some of the different solid state electrodes. So we've talked about lanthanum fluoride, and it will respond to fluoride, but notice it also responds to lanthanum. That's not something we commonly want to measure, but you never know. Another common one, silver chloride, will respond to both silver and chloride. And then notice there's silver bromide, silver iodide, and silver sulfate that will all respond to those ions that are in the membrane. There are some that are mixed. So notice we take silver sulfide and mixed it with some copper sulfide. That'll respond to copper. And there's one for cadmium and for lead. Okay, so those are the solid state. Here's another table that just shows you some of the ions we can measure with these solid state electrodes. And then they show you some different ions that will interfere with those. So notice we said fluoride, OH would interfere. Notice that they give us the kind of the range of concentrations that you can measure. And most of them are, 10 to the -5, -6, -7, this one -8. So those are kind of your lower end. So we do want to ask the question, well, why are they different? Why do these have different detection limits? Well, the detection limit is determined by the solubility. Okay, remember I said that that membrane cannot dissolve in your solution. Okay, but that membrane, and we said, it can't go into your solution. But the reality is all of these will dissolve a little bit. Now, they don't dissolve much. These are insoluble ions. Okay, all of these that we looked at, these do not easily dissolve, but all of them dissolve a little tiny bit. And you've studied that chemistry. Do you remember what you talk about to determine how much is going to dissolve? You remember this thing called the KSP, the solubility product constant? And that will tell us how much silver chloride will dissolve into water. So the KSP for silver chloride is about 10 to the -10. So remember that means the solubility is going to be 10 to the -5. So if this is made of silver chloride, this membrane over here, then 10 to the -5 silver and chloride are going to go into that solution. And that means I cannot measure concentrations above that. Okay. So those different detection limits, that's where they come from, is the solubility. If you mix the crystal, I showed you those ones that had the silver sulfide with copper, then that will improve the solubility, but it's always going to be a limitation. One other thing that you have to be careful about is sometimes these membranes get poisoned. Like if we've got silver chloride and there's, say, some sulfur in solution. Okay, well, sulfur loves silver, so it's going to come up to that electrode and react. And then you're going to get this film on the surface and that membrane doesn't work anymore. So if that happens, then you actually have to polish them. You just take a special kind of cloth and usually aluminum oxide, and you just polish it to wear off the contamination. Okay, so that's the solid state electrodes. Okay, let's see how we're doing on time. Okay, so we have time to do a little bit more. Okay, so let's talk about the instrument to do this. So we said we are going to be measuring E cell of galvanic cells. We're measuring voltage of these spontaneous cells. Now we need to think a little bit about the IR drop. Remember we said that's one of the things that affects E cell, because we have cations and anions moving through a solution, and so there's going to be a resistance. And we actually don't want to have to deal with an IR drop. So in order to keep this term small, what I want is for I to be very, very small. Okay, it can't be 0, but it can be very, very small. Okay, remember I said at the beginning, we measure this where the current is negligible, very small. Now, how do I make sure the current is small? Well, I do this by making sure that my meter has a very high resistance compared to the cell. Okay? And that will mean the current in your solution will be small. Okay? So what does that look like? Well, it looks like this, what you've seen in the lab. Now, you can't see the inside, but if you could look inside, we would find out that the resistance of this meter is much, much higher than the resistance of the cell. And again, what that does is makes this current negligible. Okay, so we do these measurements with almost no current flowing. Okay, so to measure potentiometry, these are very fast, simple methods. In theory, all we have to do is to compare a standard solution, and we don't have to remove my analyte, and we just use these simple equations. Now, we've been talking about this one. E cell is a constant minus 0.0592 over n px. This would be if you're measuring a cation. If you're an anion, if you're measuring anions, that sign actually changes. And the reason has to do with how they connect them to the meter, so that your signal and concentration are changing in the direction you want. You don't really need to worry about whether it's plus or minus. You'll know when you use it. So you can really just think of it as one equation that it's either plus or minus, but you don't need to worry about which. Okay, so one way to do a measurement is to simply determine K. Okay? And we can do that with a standard. Okay? In theory, you could take one standard, and remember, a standard, I know its concentration, I measure E cell, and then I can calculate K. And then I can use that same K for everything. So this would be a very fast, direct way to make measurements. But this assumes that K does not change. And this actually is not a good assumption. K does change. It depends on the junction potential. In addition, these equations are for activity and not concentration. So if you do it this way, just one standard, you're likely to have some errors. This really is not the best method. So what is the best method? Well, our old friend, the calibration curve. So, calibration curve, we're going to make a curve. And we've already talked about this a little bit. Looking at this, what am I going to plot? Okay, signal, which is E, and here, concentration. And you can't just say concentration, it has to be p-ion. It has to be minus the log of the ion. So we're going to make a plot, potential versus p-ion. And often the units for potential will be in millivolts. And if you have a 1 electron transfer, what is going to be the slope of this line? Okay, well, we've already talked about that. It's going to be that minus 0.0592, either plus or minus depending which way things are connected. Now, notice here it's using 59. This is millivolts. This is volts. Okay. All right. So the slope will be either plus or minus 59 millivolts. So there is actually one of the homework questions in your book that just asks this exact question. So it says, what do we graph to give a linear relationship between concentration of analyte and potential? Okay. And then what's the slope for 1 electron and 2 electron? So we just talked about this. What do we graph? We graph, there's your equation, the graph, potential on the y-axis, and p-ion, or minus the log of the ion, on the x-axis. Okay, if you have 1 electron, then that's 59 millivolt slope. And how about for 2? Okay, well, no, 0.0592 divided by 2, so that one's going to be 29.5. Okay? All right, so now how many times have I asked about this calibration curve? Or talked about it? Several. Okay, so this is actually this is one of the most important points from this chapter. It's how we use it. Is how do we make these graphs? Okay? 1 electron transfer or 2 electron transfers. Okay? And in fact, in your homework, there is a calculation doing just that. Okay, so they're using a fluoride selective electrode. And notice they measured 3 standards, and then they have all these unknowns that they're measuring. Okay, so they ask you, again, what kind of relationship should there be between E and the concentration of the fluoride? And again, we've said that we're gonna make a plot of E versus minus log of the fluoride, and that should give me a straight line. Okay, then they ask you to actually plot the data to find the best straight line. So for your homework, I actually want you to do this. You're going to have to use Excel or something, but as engineers, you have to know how to plot data. So you need to actually go and take these top measurements, and you need to make a graph, and you need to get an equation for that line. And you need to give me the graph and the equation as part of your answer. Okay, and then they want to know about these samples. Are they within a certain level? Okay, so notice that these measurements for these are all in molarity. And they are asking now, are they within a ppm range? Okay, so ppm, is that the same as molarity? Not at all. Remember, molarity is moles per liter. ppm, that's a mass divided by total mass. So if you have a dilute solution, which this is, that is equal to milligrams per milliliter. Okay, so you're going to need to convert moles per liter to milligrams. Convert moles to grams. You should know how to do that. Okay, so your homework is to do 3 and 4. And then that problem that I just talked about, 12. You don't need to do A, but B, C, and D. And you'll turn these in on RAIN. Okay, for 12, you need to give me your graph with the equation of the line. And this cannot be one that you draw. You need to do it in Excel or some other program to get the equation for this line. Okay, so that's going to be the first part of your homework. Okay, the second part is to register your attendance, and we're not going to do it here. You're going to need to send me some information. Okay, so let me tell you what you need to do. We need to actually start thinking about the final exam. As I told you, the university requires that final exams be monitored. You can't just take them like you do for the quiz. We tried to do this in RAIN, and many of you couldn't make it work. So we have to use another method that may be more painful. So for the final, you're going to need to use RAIN to do the test, and you have to do that on your computer. And then you also need to use Zoom. And so you're going to use your phone actually on Zoom. And the phone's actually going to be taking a picture of you taking the test. So I have prepared a document about this. And after class, I will send it to the WeChat group. And so I need you to read this document to make sure you understand it. Okay, the other thing, we need to start thinking about a time for the final exam. Our last class will be the week of December 25th. Our class is actually supposed to be on the 25th. We'll see whether we do that or not. I know that's a important holiday for a lot of you, not all of you, but a lot of you. So we'll need to have the final either the next week after that or week 19. So looking at your schedule, some of your classes have finished, some go a little bit longer, but it looks like the most open times are Tuesday and Thursday. So we can either have the test during week 18 on Tuesday or Thursday, or week 19 on Tuesday or Thursday. The test will need to be in the afternoon because that's the best time for everybody that's all over the world. For this test, everybody must take it at the same time. There will be no exceptions. Nobody gets to take it early or later. Everyone has to take it at the same time. So it will be an afternoon test. Okay, so for your attendance for this week, okay, this is what you need to do. You need to read this document that I'm going to send to WeChat, and then everybody sends me an email. Make sure you give me your name and your student number. Don't just send the email. I don't know who you are. And you need to tell me two things. One, you need to tell me that you have read this document, and then let me know if you have questions or problems. Okay, two, you need to give me your preference for the final exam. You know, what time, what day would you like to have the final? And again, these are the options. And if you have any conflicts, you need to let me know. Okay. Now, by conflict, I mean, oh, we have another test at that time, or we have a class. If you have something of your own that you have arranged that is not related to your Tianda classes, then that's not an excuse. You guys are sorry, but you guys are supposed to be students, and your time is supposed to be dedicated to studying. Okay, so you know, if you just say, "Oh, that's my day to go shopping. I can't do the test." Sorry. Okay, so if you have a legitimate excuse, like another test, because I don't know when your tests are, you need to let me know. Okay. I am willing to listen. You know, if you say, "Oh, we have 3 other tests this week," you know, can we have it week 19 or whatever, but you need to let me know, okay? So from everybody by next Monday, I need to know you've read this document and your thoughts on the final exam, okay? Okay, so that will be it for today. So as usual, I will wait for questions, and then after class, I will send the information in WeChat. I will send the homework answers. Eventually, I will send the video, but that always takes a couple hours. Okay, so any questions about anything?
Hey, teacher.